this is an actual exam I gave in my statistics course. It's about hypothesis testing and estimating population proportion or population mean. Let's start with number one, where there's a survey where 6,948 adults say extreme weather events are happening more often, and this is among the 10,371 surveyed. The first question is about the point estimate of the true proportion. And you have to understand that what's at hand is some result from a sample, and what you really want to know is the true proportion of adults thinking that extreme weather is happening more often. Of course, the best way to find the exact result would be to survey every adult living in the United States. However, that's going to be impossible, and also it will cost a lot of money. So in most cases, what you end up having is just a sample of the population that you want to know about. So since there are 6,948 out of 10,371, from the sample, the value that we get is, if you use the calculator, let's see, 6,948 divided by 10371, and it gives you 0.6699, which rounds to 0.670. And so you get 67.0%. That's the sample proportion, but since that's the only data that we have, there is no reason for us to believe that the true proportion should be bigger than this or less than this. So this is like our best guess at the true proportion. Now, however, because this is just a guess, it should come with some margin of error. The nice thing about statistics is that not only gives you this simple estimation, but it also tells us how confident we can be about this result. So the margin of error formula should be used, and the formula that we're going to use is this one. Now, there are margin of error formulas for estimating population mean, and there's something for estimating population proportion, and you have to know which one to use. The P and Q are the ones for the proportion. And we also need to know what each of these variables mean, where P hat is already given to us from part A, but Q hat, by definition, it's the 1 minus of P hat, so 1 minus 0.670 gives you 0.330, and that's what we will use for Q hat. N would be the sample size, because we surveyed 10,371 people. That's the value of N. And what requires a little bit more work is this Z alpha over 2. And it's done as follows. First, you have to find the value of alpha level, or it's also called significance level. Significance level is 1 minus the confidence level, and because we have 95% confidence level, it must be 1 minus 0.95, which is 0.05. Once you get the alpha level, then to find the critical value for Z, to get the critical values, you have to use the inverse functions. And since Z is for the normal distribution, we are going to use the inverse norm of 1 minus alpha over 2 in the calculator. Or you can also look at the table to figure this out. But either way, you will see that it's going to be 1.96. So let me briefly show you how to do this in the calculator. You do second distribution, you go to inverse norm, and you punch in 1 minus 0.05 divided by 2 as the area that you want, and if you paste, and you get 1.9599, which rounds to 1.96. So that's what I got. And since I have all the values I need, I can just plug them in to find the margin of error as this value. And if you use the calculator to find that, let's see, 1.96, then square root of 0.670 times 0.330 divided by 10371. I get 0.00904, which is like 0.009. Okay, so we have 0.9% as the margin of error. Now, what does that mean? That means that although we only have a sample and we don't know what's going to change if we sampled everybody in the United States, if our survey was done right, that the 10,371 adults were randomly selected and it's a good representation of the entire population, then we can be confident that at most the true population would be 67 plus 0.9, which is 67.9, and at least it'd be 67 minus 0.9, which is 66.1%. So the true proportion, true probability of, or true proportion of adults believing that there are more extreme weather happening recently is between 66.1% to 67.9%. And we know that with 95% confidence. So, I mean, it could be that somehow our representation was poor. Just by chance, we got a value that was skewed towards to one or the other, but that would happen less than 5% of the time. All right, so that's what we get for the margin of error. Let's move on. Okay, what is the confidence interval? Well, for the confidence interval, as I said, you add or subtract this value, and if you do that, you get 0.661, and then probably P is the actual probability of the population, or proportion of the population, and then 0.679 is the maximum. So that's the confidence interval. Your P should be between these two values. Okay, second question. A news organization wants to report on percentage of workers that are working remotely, and then they want to know this with the margin of error being 3% or less, and with 95% confidence level. So the question is, how many samples will they need? And this is actually a very important question for anybody doing surveys, because that's money, right? Getting each sample requires money. Sometimes you can go with something cheap, like randomly dialing people, but a lot of times you may have to hire workers to like repeatedly try to contact someone and try to pursue that knowledge, right? Okay, so the question is about how many samples. So for this, let's go back to the formula for the error, or the margin of error, which is this one. And because we're looking for the value of n, that's the sample size, what we want to do is we want to take this and solve for n. So if I solve for n, so first divide by z alpha over 2, and then square both sides to get rid of the square root. And then you can flip left side and flip the right side both upside down. So I flip them. And then finally, if you multiply p hat, q hat both sides, this is the formula for the number of samples. Now, it happens that this p hat q hat would give you the maximum value if it's 1/2 1/2, and if you have some other values, then you would have a smaller value for n. And here's a dilemma. See, in order to figure out what n is, you need to know what p hat is. But p hat is something that you obtain by doing the survey, right? So before you do the survey, you don't know what p hat is, and therefore there's no way to get the n. But you want to know the the value of n before I do the survey. So there are two ways that we try to address this. One is like if you have totally no idea what p hat and q hat would be, then just think of p hat as 1/2. Then q would be 1 minus 1/2, which is 1/2. And that gives you the maximum value. So it gives you how much samples you need in the worst case scenario. But in some cases, there will be some other surveys of similar type before, and they might give you an idea of what p hat and q hat could be. And if you have that, then you can use that value in place of 1/2, 1/2. Okay, so if you have no idea at all what to use for p hat, q hat, just use 1/2, 1/2. But if you have some ideas, then use that value. And for us, because another survey that was similar was given to us as 65%, we can use this as 0.65 and q hat as 0.35, because 1 minus 0.65 is that. So we put those numbers in. We already know that at 95% confidence level, the z critical value is 1.96. We just did it a little bit a moment ago. And then we have the value for the e. We want it to be 0.03. So plugging in all the values, you get 971.07. Now there's still one more thing that's really important. You can't collect exactly 971.07 samples because this is usually people, and you can't have a 0.07 person. And therefore, whenever you get this result, you always have to round up. That's really important. Okay, so rounding up, we got 972 people. So 972 is the correct answer. If you write 971, then it wouldn't be full credit, okay? All right. Next question, number 3. A local grocery chain is trying to order some apples, and before they order the apples, they want to have some samples to see what kind of apples they're getting. And they got 60 apples from a box and measured their diameters, and the result was that the size was like 3.75 inches in diameter, and standard deviation of the values, because not all apples are the same size, they would be slightly different, and the standard deviation came out to be 0.5. And the first question is, find the confidence interval for the average diameter of apples that they will be getting at 0.05 significance level. Yeah, so first of all, if 0.05 significance level is same thing as saying 95% confidence level, because significance level is 1 minus confidence level. And so we want to estimate the population mean, or the mean value of the entire apples of the farm with 95% confidence. And of course, without any more analysis, the best value is just 3.75. That's what we can say, but that comes with some error. And what we are interested in is how much error it could be. And we can work that out by using the standard deviation of this sample. And because this is about estimating population mean, we need to use the formula for estimating population mean. And this is the formula. It's almost same thing as the estimating population proportion, where instead of sigma you have square root of PQ, P hat, Q hat. And they're somewhat related because the binomial distribution has standard deviation square root of NPQ, and it's like n is being 1. But anyways, you just have to know which one to use. So for our case, we use this one because this is for the estimating population mean. If you estimate the population mean to be 3.75, there could be some error, and the margin of error is given by this formula. All right, so For 95% confidence level, we already know the z critical. It's 1.96. I just made the same value so that we don't have to do this over and over again, okay? And then the sigma is given, this is standard deviation, which is given as 0.5. And n is given as 60 apples, because that's our sample size, right? So we just use those values and plug in, and we get E equals to 0.127. Okay, so we got the margin of error. Now, how do I find the confidence interval? Well, margin of error is how off your estimation can be, and your estimation is 3.75, right? So at most, the diameter would be 3.75 plus 0.127, and at least the diameter would be 3.75. The average diameter would be 3.75 minus 0.127, and therefore we have to do these two calculations, and adding and subtracting, we get these two values. Okay, so that is where the population mean would be at. Okay, the population average, or the average diameter of all the apples from the farm, would be somewhere between 3.62 inches to 3.89 inches. Okay, next question. If the sample of apples were from the same tree out of hundreds of trees they own, would you be able to trust your result in part A, this part, more or less? Explain your reasoning. Well, I would trust less, and the reason is, if you just have one tree, that tree could be somewhat different from other trees. It could be in a place where it gets it's near a river and it gets more water somehow, or maybe some animal was dead under the tree. That sounds gross, but it does give a lot of nutrients to the tree, right? So it might make the apple sizes bigger for that one tree. So I would say I trust less because the sampling method is cluster sampling, right? You're only sampling from one part, and it may not give a good representation of the whole population, because if the people working the grocery store visited the farm and really brought back 60 apples from various different trees or different boxes, then it's more randomized, and you would expect it to be more a better representation of the entire population. Okay, so I would trust it less. Okay, number 4. So there's a grocery chain again, and this time it's about avocados, and this company Appeal is saying that they have a new coating which will increase the shelf life of avocados, and it should be more than 7 days. So they did some experiments, and this is how long the avocados lasted. And here's what we have. We see that these numbers have sample mean of 8.08, and the Bessel corrected standard deviation would be 1.73. Bessel corrected just means that instead of dividing by n, you divide by n minus 1, because that's closer to the population standard deviation. And the question is, with this data, can you support the claim that average shelf life of treated avocados is more than 7 days? Use the 4-step process to test the claim at 95% confidence level, which is the same thing as 0.05 significance level. See, 95% means 0.05 significance level. All right, so just by looking at the data, I mean, there are a few avocados that did not last until 7 days, but a lot more lasted more than 7 days. And the average did come out to be more than 7 days. So it's good, right? But we just want the statistics to handle this and give us a better idea of how much you can trust this result. All right, so it says to use the four-step process. So it's very important that not only you know how to answer this, but also you have to know the four-step process. Okay, so let's start with the first step. Step one is to state the hypothesis, and by hypothesis, I mean the null hypothesis and alternative hypothesis. And the null hypothesis is always in the form of mu equals to a value. Okay, so whether it's the hypothesis on population proportion, hypothesis on population mean. Also, later in this class, you're going to learn something called the Rho test. Those three tests have the null hypothesis that look like mu equals to 7. On the other hand, the null hypothesis for, say, chi-squared test for independence, that has a completely different formulation, so there are exceptions. You also have to take a note of that, but at least you have to know that when it comes to testing for population mean, the statement is always mu equals to some value, right? And the alternative hypothesis is what we want to prove, and we want to prove that it's more than 7 days, so we use this inequality. Alternative is always one of the three. It's either mu not equals to 7, mu less than 7, and mu more than 7. And because we want to show that it's more than 7 days, we would choose mu more than 7, or if written according to the question, it means that the shelf life of the avocados will be more than 7 days. That will be the fully written alternative hypothesis. Sorry. I should really have said average shelf life. Okay. Yeah. Because it's about population mean or population average. So I should have said population average shelf life. Okay. If you just say shelf life is more than 7, then we clearly have some cases where it's not more than 7, right? But the company is claiming that average shelf life is more than 7. Okay, so now let's go move on to step 2. In step 2, so let's put that in there. Okay, we have to find the critical value using t-distribution. And the reason we have to use the t-distribution is because the sample size is less than 30. We have 12 avocados, right? So it's less than 30. Okay, and to do that, we have to know we first have to know the degrees of freedom, which we didn't need when we were trying to find the critical value for z. In that case, you don't need the degrees of freedom, but we do need to find the degrees of freedom if we are to use the t-distribution. Okay, and 12 minus 1, 12 is the value of n, so we got 11 as the degrees of freedom. And then we have to find the critical value for this hypothesis testing. And one thing that you have to notice here is that because we're testing whether the average is bigger than 7 or not, we actually have to do a one-tailed test rather than 2. So this is important. This really means one tail, right tail test. Okay, that's what we need. And for one tail, right tail test, here's what we are trying to do. We want to find this critical values somewhere here, so that the area is the given significance level, which is 0.05. So I want this area right here to be 0.05. And for that to work, you have to use the inverse t. Always finding critical values, you need to use an inverse t or inverse norm or inverse something. And for this inverse t, we have, it gives you the, so there are two ways. One is you can just plug in the alpha itself as 0.05, but then it's going to give you the negative value. See, if this is 0.05, this remaining part is 0.95, right? So if you ask for inverse t 0.95 with degrees of freedom 11, then it will give you this critical value, because the area that you have to plug into inverse t is not the right tail, but the left part of that critical value. That's how it works. Okay, so let's go to the calculator. And we are going to go to distribution, inverse t, and we are going to put 1 minus 0.05 with degrees of freedom 11, and that gives you 1.7958 or 1.96 if you round it. So this is what we get, 1.796. Next, we have to compute the test statistic, the value obtained from the sample, so that you can compare with this critical value. And the test statistic is usually called a z-score, but it's the same formula, but this time we call it a t-score because we're using the t-distribution. T-distribution is a little bit wider, and it's invented by, it's called student t-distribution, and it's invented because if you don't have enough samples, you get some additional penalties. So this t-distribution is a bit more wider. All right, so this is the formula, and we have all the values. X bar is 8.08, mu would be 7 right here. S would be this one, 1.73, and divided by square root of n, where n is 12. So you can just compute all of these values, put everything in here, and that gives you 2.16. And as you can see, 2.16 is bigger than 1.796, so it's on the right side of the rejection region. See, so we have this 1.796, where it's the critical value, and on the right side of this you get this 0.05 area. So this is our rejection region, and because 2.16 lies in the rejection region, our conclusion is that we can say that this sample is a good enough evidence to show that the null hypothesis is wrong. So it's a good enough evidence to reject the null hypothesis, and that's why you have to write on the conclusion. That's step 4, okay? And you can write like this: since 2.16 lies in the rejection region, we reject the null hypothesis. So there are two statements you should always try to have in the conclusion of a hypothesis testing. Is first, you have to say either you reject the null hypothesis or you fail to reject the null hypothesis. One of those two statements should be there. It's either one of the two. There are no other cases. And then you want to elaborate on what that means by using the context. So here, rejection of the null hypothesis means that the alternative hypothesis is correct, right? And you have to state the full alternative hypothesis, and here's the result. We have sufficient evidence to support. And by the way, always try to use this language: sufficient evidence to support. We're not proving things. Proof would be, in mathematicians treat proof as a word that you only use when it's a definite proof, okay? So for us, when we have evidence that supports a claim, we're careful to just say that. Okay, so we have sufficient evidence to support that the shelf life is more than 7 days at 0.05 significance level. So if you write that extra, that would be even better. Okay. All right. Question 5. Each part is independent of the other parts. I think this should have been question 4. It's numbered incorrectly. But anyways, first, a 90% confidence interval for a population proportion is given as 0.49 to 0.74. Find the point estimate p hat. Well, for this one, here's 0.49 and here's 0.74. And the way we get the confidence interval is by first obtaining the sample proportion, and then we calculate the margin of error, and we add the margin of error E to get to this highest value, and we subtract the margin of error E to get the lowest value, right? And because of this, the picture suggests that p hat would be just exactly the midpoint, right? So all you have to do now is to just take the average. So let's add the two numbers, parentheses 0.49 plus 0.74, and then you divide by 2. And it gives you 0.615, and that will be the answer, 0.615. Okay. Next question. For a hypothesis testing of mu equals to 70 and mu not equals to 70, if something is not equal, this is a two-tailed test, okay? And for two-tailed test, you have to double the p-value, okay? Double the probability, because they're two tails, right? If it's a one tail, you just calculate whatever, but here we have to double. Okay, so here's what we have. We have 2.31, and the p-value is, for 2.31, we first have to figure out the area after 2.31, and then we have to double it because it's two-tailed test. Okay. Somehow the sample size 200 is irrelevant because the z-score is the only thing that we need to find the p-value. All right, so let's do this. First, we can use the normal CDF to get the area between, this is negative infinity, until 2.31. And if I paste it, you get 0.989555, but that will be this area, right? 2.3 and afterwards, it'll be a very small area, and that would be 1 minus this area, so we should really do 1 minus second distribution of the normal CDF, and we paste it, and we get 0.01044, okay? So 0.01044. And now you have to double this because this is a two-tailed test, as I said, so your answer will be 0.02088. Okay, so that is the value of the p. Okay, now part C, set up the two hypotheses in symbolic form to test the statement. The average viewing time of Netflix viewers is above 600 hours this year. Use either p or mu. Okay, so here you first have to figure out whether this statement is about population proportion or some average value of some quantity, and it seems like it's the average value of some quantity, which is the mu, right? P is like the population proportion. So we're going to make a statement about mu. Let's see. So H0, and we say mu is equal to 600, because the null hypothesis should always be stated as mu equals or p equals. And H1 is what you want to prove. You want to prove that it's above 600. So you want to say mu greater than 600. Okay, and that's it. This actually shows you that these two are the null hypothesis and alternative hypothesis to do these claims. Of course, after this, you will need some data to verify this, but these are the hypotheses. Okay, part D, if a sample in a hypothesis testing is 0.05 significance level and the p-value is 0.07, which of the following is correct? Well, see, if you have a bigger value than the given significance level, then you don't think of this as some unlikely thing happening. The core argument of the hypothesis testing is that if you assume that the null hypothesis is true, then the current sample is a very unlikely event, so we reject the null hypothesis. That's the core of hypothesis testing. But there's always this question of what do you choose as what do you choose as unlikely event, and that level is called the significance level. And only when it's below the significance level you say we have an unlikely event happening, which allows us to reject the null hypothesis. But here 0.07 is bigger than 0.05 significance level, so in this case we fail to reject the null hypothesis. That's what's happening. Okay, so there is insufficient evidence to reject the null hypothesis. So this is it. Okay, either we fail to reject the null hypothesis, or we have sufficient evidence to reject the null hypothesis. Those two. Okay, we can never accept the null hypothesis in a hypothesis testing. We can only say whether it's wrong or whether we don't know if it's wrong. We cannot say it's correct. All right, and the conclusion is you never reject the null hypothesis or fail to reject the null hypothesis. Okay, so the answer for this will be C. Okay, last question. Semiconductor fabrication company bought a machine for etching chips, and they have a new machine, and they looked at the data, and it seems to suggest, well, look at this, it has less bad outcome and better good outcome. Like if you can have one wafer giving you 140 chips or more, that's better, because even if you etch these chips on wafers, they a lot of times have errors, and if they have errors, it's no good, so you throw them away. So having a lot more chips successfully etched would be a good thing for the company. So they got this data, and they're wondering, hey, is this new machine somehow much better than the old? What's going on? Okay, so they want to test this out. Okay. All right. So state the hypotheses to use for chi-square test for independence. And here you have to know that the null hypothesis for the chi-square test is a bit different. So the null hypothesis is saying that there is no relationship between the number of chips etched on wafer and the machine being old or new. Okay, and H1, of course, the alternative would be the opposite of this. So there is some relationship. There is some relationship between the number of chips etched on wafer. Yeah. So to say it in a roundabout way, what we are trying to say is that the ratios change when you switch the old machine to new machine. And it's statistically significant. That means that the performance improvement you see is not just by pure chance, but it's really due to the machine being new, and it has some better tweaks that made it better. Okay, so these are the hypotheses, and now let's move on to B. What is the expected value for the old machine and 140 chips or more cell? And the old machine and 140 chips or more with this 71. The expected value that should be in here, if these values were given purely by chance, is computed by this formula. Expected value of a cell is the row total, which is 200, and times the column total, which is 160, and then you divide it by the grand total, which is 400. So this is going to be 200 times 160 divided by 400. Now let's do the calculation. 200 times 160 divided by 400, and that gives you 80. So that 80 is the expected. Now there is another way to figure this out without using the formula, so I want to introduce you to that. And the way you do it is first go to matrix, and you can edit. Oh, not that. Quit. All right. Go to second, and then matrix here, and then you go to edit and edit A. And what you want to put in are not the totals, only the data itself. So this is like 2 rows and 3 columns, right? So you want to put 2 by 3. And you want to put these numbers in. So these are 71, 82, 47, 89, 77, and 34. And then you can quit out of it. And now what you can do is you can go to stat and go to the tests with chi-squared test. So you can go to the chi-squared test, and observed data is this is the observed data, right? And it is in fact A, right? And for expected, just leave it as B, and you don't have to worry about it even though we didn't do anything to B. This B matrix will be populated by the expected values. So you can calculate this, and you can see that the degrees of freedom is 2, chi-square is 4.268, and the p-value is 0.1183. And actually the p-value tells us something more. We know that at 0.05 significance level, we cannot reject the null hypothesis. And therefore, we cannot say that there's a relationship between old and new. Okay, so having this at hand is really helpful for solving the question. But since this question is just about the expected value, let's go to matrix B and see what's populated there. And if you look at it, the expected value again at this top left corner value is 80, right? So our calculation 80 was correct, and the calculator does agree with us. Okay, so that's another way to get this value. Okay, next question. State the degrees of freedom and the critical value at 0.05 level. First of all, the degrees of freedom is 2 just because the calculator gave us that. So let's go back to stat, tests, chi-squared test, and enter degrees of freedom is 2, right? And the critical value at 0.05 level requires the use of the chi-square table. So you can look for any kind of chi-square table. I just googled one, and here's a chi-square table. And as you can see, degrees of freedom 2, and at 0.05 significance level, you get 5.991 as the critical value, right? So this will be 5.991, and the degrees of freedom will be 2. And if you don't know how to use the calculator, the way you get the degrees of freedom is just look at this data only, not the total. And it has 2 rows, so and 3 columns, and you subtract 1 for each and you multiply. So it's 2 minus 1 times 3 minus 1, which is 2. That's how you get the degrees of freedom. Okay. And now, because the chi-squared is less than the critical value, since 4.269 is less than 5.991, the critical value 5.991, we fail to reject the null hypothesis, and therefore we do not have sufficient evidence to prove that the new machine, the machine being old or new, is related to the performance. Okay, but our intuition tells that they should have, right? So I think what's going to eventually happen is that they just did the 200 wafers, right? If they increase this wafers to 400 or 1,000, they're going to see numbers that are bigger, and with more samples you can get a better idea. So even if the numbers are just proportionally bigger, if the sample size is bigger, then you will be able to say later that yeah, the new machine is indeed doing better. But at this point, the data that we have could be just by chance, so we have no idea whether it's really sufficient. I mean, we have no idea whether the new machine is really doing well or not. Okay. All right. So contrary to our intuition, there is no sufficient evidence. This data is not statistically strong enough to support our claim. Okay. All right. So here's yeah. So actually, we actually did that. Draw the correct conclusion to determine if there is a relationship, and that's what we have. Okay. So sorry. For the decision rules with values, it's that if chi-squared is bigger than what was it, 5.991, then what you do is you reject null. Okay. But if it's less, then you would fail to reject null. Okay, so that's what happens. Yeah. And that's all the review of the second exam I gave.